Hello class, welcome to this lesson on 4.8. We're going to be talking about combinations and probabilities today. So we want to be able to determine how can we compute combinations as well as use them with the multiplication counting principle in order to compute probabilities. So we're going to talk about combinations and how to actually calculate them. We're going to use these combinations to calculate probabilities as well as the multiplication principle in tandem with combinations. So the new vocab term is going to be the combination. So recall that a permutation involves an arrangement of objects in which order matters. For example, selecting students for ranked positions or selecting baseball players for the batting order. In that case, for ranked positions or batting order, the order actually matters in which you select the individuals. So sometimes we're only interested in finding the number of ways to choose some individuals in a group, not necessarily caring about the order in which they're selected. You just want to make a selection. So suppose that Mr. Soto decided to randomly select 3 students' homework papers from his class to grade each day. There are 28 names in a hat, and 3 names are drawn one at a time. So in this case, you would probably be tempted and say, okay, well, there are 28 names, and then 3 names are drawn. So based on off of the previous lesson, we could say that, well, if I choose the first name, I got 28 choices to choose for the first name. So in this case, you would say, well, this is going to be 28. And then for the second, once I choose that name, I got 1 name left, and that leaves me with 27 names to choose from in the hat. And in this case, I have yet 1 less name to draw on the hat. And then by the multiplication counting principle, we should be able to multiply those ways to get the total number of ways. However, this is only half of the story, because the 28 times 27 times 26 here, the number that you get, is actually based off of the order, in which order matters. So this is just only representing the number of permutations, essentially. So remember that this is only the permutations of 28 chosen 3 at a time, and this is only when order matters. So if we want it where order doesn't matter, then that means we're going to have a lot less options. Because, for example, if Mr. Soto picks Alana, Nate, and Brooke from the hat, well, there's no difference in getting, for example, Nate, Brooke, and then Alana, because we're talking about order not mattering. So it doesn't matter if those names are switched out. It only matters the actual names that are pulled. So how many different ways are there of mixing these names? So if we want to figure out the number of ways of mixing these 3 particular names, then, well, let's go ahead and list them out. You can do Alana, Nate, and Brooke, or Alana, Nate, Brooke, and Nate, Brooke, Nate, Alana, Brooke, Nate, Alana, Brooke, Alana, Nate, and so on. You have a total number of 6 ways. So there are 6 ways of mixing these particular names and no other names. So what we just did is the permutation of the 3 objects, right? Of those 3 objects in particular. So for the first name, I have 3 choices. For the second name, I have 2 choices. And for the first name, I got 1 choice left. So in this case, there are 3 times 2 times 1, or 3 factorial ways of actually mixing these 3 names, or 6 ways. Now remember that the order in which Mr. Soto chooses the 3 papers doesn't actually matter. So to avoid counting the same group of 3 individuals 6 times, which is what I found on top here, we have to divide our original incorrect answer by 6, which is exactly what we got on the top. So, recap. The permutation with 28 and 3 is actually just the number of names, or the number of ways that I can choose the names 3 at a time if we're taking into account order. If I want to not take into account order, well then I need to divide by 6 to ensure that I'm not counting the same individuals 6 times, the same group of 3 students 6 times. Therefore, eliminating those ones in which order doesn't matter. So we can take our probability of 28 chosen 3 at a time, and then we can divide that by 6. In this case, well, the 28 chosen, or the 28 permutations 3 at a time, it's going to be 19,656 divided by 6. In this case, we have 3,276. Okay, so recapping again, we got 19,000 because order matters. If we want to prevent order from mattering in this particular count, we need to divide by the total number of ways that you can actually arrange those 3, that you can actually pick those 3 together in order to divide off the extra count of individuals, and therefore we get only the counts in which order does not matter. So the result gives the number of combinations of 28 students taken 3 at a time, which we write as either 28 with the C and then 3, or we use the parentheses notation with 28 and 3. This is actually pronounced as 28 choose 3. So if I say 28 choose 3, that's just simply the combination here, or this. So this in particular is pronounced 28 choose 3. All right, so a combination, and let's go ahead and change this K into R. So a combination is a selection of individuals from some group in which the order of selection does not matter. If there are n individuals, then the notation n and c with r represents the number of different combinations of r individuals chosen from the entire group of n individuals. So we're just doing a selection of individuals in which order does not matter. So in order to do that, remember from our previous example that if you wanted to find it without where order doesn't matter, well, first you're going to have to figure out, you're going to have to determine the number of arrangements in which order does matter, and then you're going to divide by the number of ways in which that particular selection of group can actually be rearranged within itself, and therefore you can divide off those extra combinations or those extra permutations in which order matters. So therefore we can divide this by r factorial. So this is actually what we did in the previous example. However, there's another way that you can rewrite this, because now we know that remember that from the previous lesson that to calculate this permutation, well, there's a formula for that, right? It was n factorial over n minus r factorial. So if we make that substitution and plug that in to this formula on top, well, then we get the final combined formula of n factorial over r factorial times n minus r factorial, where if you notice, this part got replaced here because of the NPR there. So this is our other formula for the combination of n objects chosen r at a time, or n choose r. Alright, so in New Jersey Pick 6 Lotto game, a player chooses 6 different numbers from 1 to 49. The 6 winning numbers for the lottery are chosen at random. If the player matches all 6 numbers, she wins the jackpot, which starts at $2 million. How many different possible sets of winning numbers are there for the New Jersey Pick 6 lotto game? All right, so we want to figure out the total number of possible sets of winning numbers. Now, so in this case, we can choose any set of winning numbers as long as it's 6 numbers, 6 different numbers. So since the numbers have to be different, this means that we're going to have less numbers as we choose the first one and the second one and so on. But also notice that order does not matter. And that's because you can choose 1, 2, 3, 4, 5, 6, or you can choose 6, 5, 4, 3, 2, 1. It doesn't matter. Those are the same 6 numbers, for instance. All right, so in this case, we're looking at a combination, right? So since we're looking at a combination, well then we have the combination of, well, we have 49. It says from 1 to 49, so we got 49 different numbers to choose from, and we can only choose these 6 winning numbers, right? So there's only 6 numbers that you can choose from. So this is the total number of possible sets of numbers that you can choose from. So then if we use the calculation, well, this is going to be the 49 factorial over 6 factorial times 49 minus 6 factorial. And this is if like you use the formula. And then 49 minus 6 factorial is 39 factorial, or 30, should be 30, or I'm sorry, this is completely wrong, 43 factorial. So I don't need the parentheses anymore. So 6 factorial and 43 factorial. And then now we can rewrite 49 factorial as 49 times 48 times 47 times 46 times 45 times 44 times 43 factorial. We can stop at 43 factorial in order to cancel out the 43 factorial from the bottom. And then recall that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So this is how you would show your work as far as like the numbers are concerned. But you can always plug this into the calculator, because the calculator has a combination function. As long as it's a scientific calculator, most of them have a combination function. But otherwise, if you don't have that, you can always just do this. So the number of different sets of winning numbers is 13,983,816. So notice that if the order did matter here, this actually would be a lot bigger, right? So it would actually be times whatever 6 factorial is. So if order mattered in this lottery, this would be even bigger than what it really already is. All right, so now we're going to be talking about probability in relation to, counting and all that. So remember that to find the probability, we take the number of outcomes in event A, whatever event you're considering, and then you divide by the total number of outcomes in the sample space. So for the previous number, or the previous example, what's the probability that the player wins the jackpot by matching all 6 winning numbers? So if we want to win the jackpot, we got to find the total number of ways to choose all 6 winning numbers, and then divide by the total number of ways to choose those 6 numbers from 1 to 49. So notice that we already did this earlier. We did this part in the previous example. Choosing the total number of 6 possible 6 numbers is going to be given by the combination of 49 objects taken 6 at a time, or 49 choose 6. So we have equals. So we have on the denominator, we have 49 choose 6. And then for the total number of ways to choose all 6 winning numbers, well, we only want the 6 winning numbers, right? The actual set of numbers. So how many ways are there of doing this? Well, we only want the 6 numbers, so how many ways of choosing 6 numbers that are the winning numbers? Well, you want the 6 numbers, right? And you want to choose them 6 at a time. So the only way to choosing the winning numbers is, well, you need 6, and you're going to select 6. So those are the set of winning numbers. And remember that this has to be a 6 because you're choosing 6 winning numbers, and there are 6 winning numbers. So what does 6 choose 6? Well, if you think about it, there's only one way of choosing the 6 winning numbers, and that is to actually choose the 6 winning numbers, right? So this answer should actually just be 1. So if you actually calculate it, then you would get 1 for this. So there's only one way of winning, that is to win. So the numerator is basically a 1. So 6 choose 6 is 1, and then 49 choose 6, we did that earlier. That was 13,983,816. So to put this in perspective, you got 1 in almost 14 million chance of winning. So if we calculate this, we have 7 zeros, 715. So that means you got a probability of 7.15 times 10 to the negative 8. Very small probability. So very small chance that you're going to win. Notice that this is almost in the trillionth. So you got one, almost in the trillionth chance. Very small indeed. Actually, now that I think of it, with all of these decimals, we got 7 zeros. This is practically almost 0. Almost, but not quite. So let's look at another example. So we have 28 students in Mr. Wilcox's statistics class, 16 boys and 12 girls. Suppose Mr. Wilcox randomly selects 3 students' homework papers to grade. Kind of like the different example, but different teacher here. Use combinations to find the probability that all 3 students chosen are girls, and then B, use the concepts from lesson 4.5 to determine the probability. So, part A, using the combinations, which is what we did earlier. How do we go about doing that? Well, we want to find the probability of 3 girls, right? So first off, we need let's go ahead and write out what we need here. Well, we need the total number of ways, right? So we'll write this as the total number of ways to choose 3 students to begin with. So what are the total number of ways of choosing 3 students in general, regardless of gender? And then we want 3 girls. So we need the number of ways on the top to choose 3 girls. Three girls from the 12 that we have, because we got 12 girls in this particular scenario. So in this case, order doesn't matter in the order in which you choose the girls. So we want to choose 3 girls from a group of 12 girls. So that's 12 choose 3. For the denominator, well, we got 28 students, and we're going to choose 3 of them for the total. All right, so once you're used to writing these combinations or writing out writing out what you need, then it kind of follows logically. Well, okay, well then that's what I'm looking for. So now we can go ahead and calculate this. So in this case, we have 12 times 11 times 10. So we got, I'll write it out here. We got 12 factorial over 3 factorial times 12 minus 3 factorial. 12 minus 3 is 9 factorial. This is going to be 28 factorial over 3 factorial times 28 minus 3 factorial. So 28 minus 3 is 25 factorial. So here we're going to do 12 times 9, or 12 times 11 times 10 times 9 factorial. And then this is going to be 3 times 2 times 1. And then we're going to stop with the 9 factorial so we can cancel that out. Alright, same thing here. We're going to do 28, 27, 26, but then 25 factorial. 3 factorial is 3 times 2 times 1. 25 factorial is just 25 factorial, so that way they cancel. And we got this. And then with this particular arrangement, the 3 times 2 times 1 cancels because they're the same, top and bottom. And we're left with this over this. So I'm going to go ahead and write that out as like that. Now, if you didn't want to do this particular arithmetic, that is fine. I just wanted to show you some of those calculations. So it's just going to be 220 over 3,276. Of course, you know, you can do both of these on the calculator, get those two numbers right away, and then divide them. In which case, you get the same answer, 0.067. Right, so now let's look at part B. Now part B wants you to use the concepts from lesson 4.5. Now lesson 4.5 involved the general multiplication rule. So what we want to figure out as well, if we want the probability of choosing 3 girls, well, this is the same thing as the probability of a girl and a girl and a girl. So you can think of this as the and probability of, and with, event 1 and event 2 and event 3. Well, remember that if you're doing and, you're going to multiply the probabilities, right? So we're going to multiply the probability of girl, and we're going to multiply the probability of girl given that we chose girl the first time around, times the probability that we get a girl given that we chose a girl and a girl earlier. Alright, so basically it's just saying that you're multiplying the 3 probabilities for girls, right? So if you choose the first girl, well, you got 12 girls out of how many people? You have 28 guys, 28 students. And now, once you choose that first girl, well, you got 11 girls left out of 27. And then once you choose that second girl, for the third girl, you only got 10 out of 26. And so this is another way of actually doing the calculation. Notice that we get the same exact numbers. If you look at this, we multiply 12 times 11 times 10, 28 times 27 times 26. We get the same exact set of numbers in a numerator and denominator as we do with part B. Interestingly enough, and so we get the same answer, 0.067. Again, two different ways of looking at the same problem. Alright, an airline had just finished training 25 junior pilots, 15 male and 10 female, to become captains. Unfortunately, only 8 captain positions are available right now. Airline managers announced that they will use a lottery process to determine which pilots will fill the available positions. The names of all 25 pilots will be written on identical slips of paper, placed in a hat, and drawn out until all 8 captains were chosen. It turns out that the 5 that were chosen were female, and only 3 are male. Some of the male pilots not selected suspect that the lottery was not carried out fairly. So, what we want to determine is, well, we first want to figure out, well, how many different ways are there of choosing those males and females? So for part A, alright, so I went ahead and added the parts A through C, which because I forgot to include it in the problem, but for part A, we want to find the number of ways in which a fair lottery can result in 5 females and 3 male pilots being selected. So basically, whatever happened, we want to figure out, is this going to be fair? So first, we got to calculate, well, how many different ways do we have of that happening? So we want 5 female and 3 male pilots. So essentially, we want to figure out how many different ways are there of choosing the females and the males, right? So how many different ways are there of choosing 5 females? Well, the order doesn't matter here because you're just choosing 5 females. So we're choosing the females. Let's call this females, and let's call this males. So we have a total of how many females? Well, they said that there were 10 females, and we want to choose 5 of them. Now, looking at the males, how many different ways of choosing males? Well, we had 15 males. Let me double check the numbers here. 15 males, and we are choosing 3 male pilots. So we have the number of ways of choosing females. We have the number of ways of choosing males. How do we find the total number of ways? We use the multiplication counting principle right here. So this is actually using the multiplication counting principle in combination with, well, the combinations, no pun intended. So this is equal to, we're going to multiply these numbers together on the calculator, and in this case we get, well, there are 252 ways of choosing the females. There are 455 ways of choosing the males. So there are a total of 114,660 ways. In this case, 660, we'll say ways here, or combinations. All right, so find the probability that a fair lottery will result in the selection of these particular 5 females and 3 male pilots. So what are the chances of that happening, essentially? Well, the chances of that happening, well, if we want to figure out the probability that we get 5 female and 3 male, so if we want to figure out probability of 5 females and 3 male, well then on the numerator we need the number of ways to get the 5 female and 3 males divided by the total number of ways to select 8 pilots in general. Okay, so we chose 8 pilots, right, in total. We want to figure out the total number of ways to select all those 8 pilots, regardless of gender, male or female. But in the numerator, we want the number of ways to get that specific arrangement or that specific selection of 5 females and 3 males. So we already did the numerator in part A. That was actually what we calculated earlier, which was the 10 choose 5 for the females and the 15 choose 3 for the males, and then multiplying those together. Now for the total combination, well, we have 25 people to choose from, and we need to choose 8 in total, right? So that's our denominator. Now we went ahead and did our numerator, and that was 114,660 divided by the total number. In this case, the total number of making that selection would be 1,081,575, which is equal to 0.106. So that's the probability, or this is a 10.6% chance. So part C is asking, based on this answer, is there convincing evidence that the lottery wasn't carried out fairly? And explain. Well, if the lottery were carried out fairly, there is a 10.6% chance that this is likely to happen. Now, is this high enough? Or is this chance high enough to warrant that, that particular event happened, right? That's what we want to ask ourselves. So what is the cutoff for whether it's too low of a chance, right? Is what we want to ask ourselves. Well, it turns out that usually the cutoff for this is 5%. Okay, so the cutoff for whether something is considered not statistically significant versus statistically significant. So the cutoff for statistical significance is usually 5%. So this means that if the process were to be conducted fairly, if there is a less than 5% chance or equal to 5% chance of that event happening, then we say that we have enough evidence, basically saying that there's something fishy going on. There's a good chance that it is not fair. So this is usually what we refer to as our cutoff for statistical significance, which means that we have enough evidence that there is, that is statistically significant, meaning that it's probably not done by chance. So that's our cutoff for that. So in this case, we have a 10.6% chance of this happening. So therefore we would say that this is not statistically significant. So again, if we're less than 5%, this means that we have statistical significance less than or equal to, which means that we have enough evidence, like there's enough evidence. However, if it's greater than 5%, it is not enough evidence or statistical insignificance. So in this case, the 10.6% is greater than the 5%. So this means that we don't have enough evidence for this. It's not statistically significant. So we have, which means that since it occurs at least 5% of the time, we can't say that it's not fair, right? So we can't conclude that it's not fair. So not enough evidence. There is more than 10%. There's actually more than a 10% chance. It's 10.6% for this to occur. Now, if the probability was 1% that this would occur, well then, something fishy might be going on. If it's even less than that, then, if it's, like I said, less than 5%, that cutoff, you're probably going to think, okay, well, there might be enough evidence to say that since this is such a low chance of happening, probably something was rigged, or something to that effect, right? There's something not right going on here, but we don't have enough evidence, unfortunately. So this is how you would use this for determining statistical significance. We're actually going to do more with this, actually, later towards the end of the statistical unit, the course. So if you're not really quite understanding this, that's fine. Just basically know the cutoffs for significance. We're actually going to get more into this when we do inferential statistics. That's going to be it for the video, guys. I hope you learned something from this, and I'll see you in the next one.